Hello and welcome to our first set of notes. Whoopsies, hang on. Okay, that's better. Welcome to our first set of notes for our first space unit. We are finally done with chemistry and all that stuff related to it. And now we're on space. So this is the first of 3 space units that we're going to be covering. The first one is going to be mostly about space in general. We'll be starting off talking about the universe today. Then we'll be talking about gravity next week, and then about stars after that. Our second unit will be about the solar system, and then towards the end of the year we'll be looking at space exploration. So like I said, today we're talking about the universe, so that is our title. Our essential question, which should be up at the top of the page, is how do scientists describe the universe? Now, of course, we should be taking Cornell notes. So if you are not familiar with that, I know we've had quite a few new students. We should be having our page divided into 2 columns. The bigger column is for your notes themselves, all the information, any diagrams you draw, stuff like that. The smaller column is for key points, vocabulary, questions, things like that. And at the end, we do need to do a summary. So let's get started. First of all, what is the universe? Well, the universe is all of space and everything in it. It is absolutely enormous. Scientists don't even really know exactly how big it is, just because it is that big. We can't see the edge of the universe. It's that big that we can't see how far it goes. All of the objects in it, stars, solar systems, galaxies, all of that sort of stuff, there's enormous distances between them. So if you were to describe the universe using one word, it would definitely be enormous. Alright, now with the universe being so big, and us really being limited to the technology that we have, how do we measure distance in the universe? Well, the answer is something called parallax. And parallax is a little bit complicated. There's a lot of math involved in it. But basically, it is the apparent change in position of an object when you look at it from 2 different locations. So, for example, if you were to look at, say, the TV in the classroom, all right? If you're sitting in the table closest to the TV, it's going to look like it's in one position. Now, if you were to look at it from, say, my desk at the back of the room, it might look like it's in a very slightly different position. Now, it's actually still in the same place, but it appears to be in a slightly different position. Now, if we were to do a little bit of math, calculate some angles, and a few other things, we can pretty accurately estimate exactly how far away the TV is. So scientists do this with things like stars and planets and galaxies and things that we can see from Earth, whether it's using telescopes or just our eyes. They use parallax to do this. So if you were, say, we're looking at a particular star in the night sky, if you see it from here in Florida, it's going to look like it's in one position. If you were to look at it from, say, California, it's going to look like it's in a slightly different position in the sky. Again, it's really in the same spot in the universe, but it looks like it's in a different position. It appears to be in a different spot. So scientists, astronomers who study space, will measure how much the star, or whatever object it is, appears to move compared to other objects in the sky. And they'll use it to calculate the distances. And they can calculate up to a few hundred light years away. Anything further than that, it's very difficult to see, and it gets very difficult to calculate. So real quick, a light year, it is the distance light travels in 1 year. It is a measure of distance. Some people get confused by the year part of it and think it's a measure of time. It's actually not. It's a measure of distance. And that's, again, how far light travels in 1 year. And if you're curious about how big that is 9.46 trillion kilometers. That is a huge distance. Now, how do scientists describe the enormous distances in space? When you look at distances in space, there tends to be a lot of zeros. We look at things in billions and trillions, and sometimes even bigger than that. We don't deal with small numbers, really. So instead of drawing out or writing out, 20 zeros for a single number, that gets annoying. That gets a little hard to read. We use something called scientific notation, and that's used to show extremely large numbers. And this uses powers of 10 to write very large numbers, or very small numbers that are a really small decimal with lots of zeros. We use scientific notation to write it in a bit of a shorter way. We're not going to deal too much with it, but it is important to know what exactly it is. So if you see something like in the examples, like the 1.2 times 10 to the third power, well, that's not a very big number. But right below that, the 9.46 times 10 to the 15th, that is a light year. So that many kilometers, look at all those zeros. That's how many kilometers are in a light year. So scientific notation is really important to help us keep track of big numbers and to be able to write them out and read them and understand them without having to go, what is that? Is that trillion, billion, billion, trillion? And having to sit there counting out the zeros. Scientific notation makes it much, much easier. Alrighty, and I am talking a lot, so I'm going to move on and try to talk a little bit less. Alright, so what is in the universe? A lot of stuff. We've got solar systems, and these contain a star, which is the sun at the center of it, and planets that orbit around, and other objects like asteroids, moons orbit around the planets. There's a lot of stuff in there, but we'll focus more on that in the next unit. We also, of course, have stars, which we'll be talking more about in a couple weeks. But basically, stars are giant balls of gas, mostly hydrogen and helium, and they undergo something called nuclear fusion. And that's when atoms combine to form larger atoms. And this really only occurs in situations where there's a lot of pressure. Most stars are much, much larger and hotter than planets. Now, a planet is an object that orbits a star. It is large enough that it is rounded by its own gravity, and it has cleared the area of its orbit. So what that means is there's nothing else orbiting really close to it. It's on its own and a decent distance away from other objects. So there's nothing getting in its way of its orbit. What else is out there? Star systems. These are groups of 2 or more stars. Most stars are members of systems, and larger groups of stars are called star clusters. And in the picture you can see some clusters, and those are the ones that are circled. Now, one thing I want to talk about real quick is constellations. Up in the sky, if people see patterns, and they make shapes. Basically, a constellation is just us playing connect the dots with stars. And sometimes it's not just one star that we see. When we look in the night sky, we might see something that looks like one dot and one star, but it might actually be a whole group of stars that they're so far away from us that it looks like it's all one big thing together. So constellations are not the same as star systems or clusters. Very often, those constellations, they may actually contain things like planets and other galaxies, but to us, when we just look at them with our eyes, not using telescopes or anything like that, it looks like a star. So it's just another big spot in the sky that we play connect the dots with, basically. That's all a constellation is. Most of those objects are very, very far apart, not even necessarily in the same cluster or the same star system. Basically, again, they're very far apart. So a constellation, very different from a star system or a star cluster. And we'll talk more about that later. What else is in the universe? Galaxies. A galaxy is a huge group of stars. Star systems, star clusters, dust, gas, a bunch of stuff. And again, this is a huge group. Billions, even trillions of stars or star systems, star clusters thrown in there, dust, gas. It's all held together by gravity. Now, galaxies are much, much bigger than solar systems or star systems. If you look in the larger picture below, the one that says "You are here," that is a picture of our galaxy. That's the Milky Way. Now, where it's pointing at, that's where our solar system is. And our solar system, when you're looking at that picture, you can't even really see it. It would look basically like a bit of a speck or a few specks. And within that solar system, of course, we've got our sun and we've got all of the planets, plus asteroids and all sorts of other stuff, which, again, we'll talk about in the next unit. So if you're looking in terms of size, planets are going to be smallest, stars are going to be the next size up, then solar systems, then galaxies, and then the universe. And that's just in comparison, size comparison of those different objects that we've talked about in these notes. I'm out of breath from talking so much, and I'm sure your hands hurt from writing so much. Sorry. Anyways, it is time for our summary. We are done with our notes for today. Please make sure to write your summary. Make sure you actually do it. I know you don't like to, but you gotta. That's how it goes. Those are the rules. All right, and that's it.